Swayam Prabha. Digital India. Educated India.
So, we have covered quite a number of topics. I thought I shall take this opportunity to give my last or the concluding talk, which will summarize what we have done in this about 40 lectures. Firstly, the limitation is we have considered only solar energy thermal systems, and in that we try to give emphasis more for the principles rather than a particular system. And the basis for that is we try to establish what is the need for in general alternate energy sources, from which we have said that human dependence on external sources, these external sources being limited and being depleted at a faster and faster rate, people started having a look at the alternate source of energy, and out of which solar appears to be a promising option. This is sort of our introduction. So, we have gone through a lots of mathematics, and then we defined GON, that is the solar radiation on a surface normal to the sun's rays under extraterrestrial conditions on a given day, which is in terms of the solar constant GSC, which is if the surface is normal to the sun's rays under extraterrestrial conditions at mean sun earth distance. So, that is how the solar constant is defined, and this is of course the estimates are varying. It could be 1353 watts per meter square, even 1367 per meter square. As we are getting more and more or rather better satellite data, this is being revised, and then we said that Earth's declination delta is given by an equation 23.45 sine 360 times 284 plus n upon 365. Of course, I am not going to rewrite all these equations. So, more exposure will be given to each frame. Then everything is in standard time as far as we are concerned, and the calculations shall be done in terms of solar time, which is given in terms of the standard time plus 4 minutes per degree of the longitude of the location and the longitude based on which the time of the country is based, LST minus LOC by plus a E. E is the equation of time, which is again related to the day of the year by the equations E and B. So, that plus will be for the western and minus for the east longitudes. Generally, we try to define n number of angles wherein you have got a surface and it is inclined at an angle of beta, Then this is the north south axis or north south direction, and this is the west east, and it is not in general in line with north south. So, there may be a azimuthal angle of gamma, it looks like r, but that is gamma is the location or notation we have been using, and zenith is nothing but the vertical to the horizontal, which makes an angle theta z with respect to the sun's ray, and with respect to the outer normal to the surface, the sun's ray will make an angle of incidence of theta. So, that theta in general a function of the latitude, slope, and of course, the time omega and the azimuthal angle gamma is a long relation, which can be put in a shorter form as cosine theta equal to A plus B cos omega plus C sin omega, where A is this expression and B is another expression and C is cos delta sin beta sin gamma. And if the surface is horizontal, the angle of incidence is also called the zenith angle. It will be a simpler expression, which you can obtain by putting beta equal to 0 as simply cos phi cos delta cos omega plus sin phi sin delta. Now, you will find this cos theta z to be independent of gamma, because if you have a horizontal surface, the projection of the outer normal will be a point and you cannot define a azimuthal angle. And very rightly, the equation reduces to be independent of the azimuthal angle. Then we defined omega s, the so called sunset hour angle, which is cosine inverse of minus tan phi tan delta, and this is the physical time that sun will be appearing, and the number of sunshine hours will be twice omega s by 15, because it takes 24 hours for the earth to rotate. So, 15 degrees per hour. So, twice of omega s by 15 will be the number of hours that the sun will be above the horizon. Of course, this gives to some problems if phi plus modulus of delta is greater than 0, it will go to a cos inverse of a negative number smaller than minus 1 or a positive number greater than plus 1, and for which cosine inverse is not defined. This typically happens if phi is greater than 66.45 degrees, because maximum of delta is 23.45, sorry, this should be 5 phi. So, anywhere beyond this latitude, you may have a 24 hours no sunshine at all, or all the 24 hours sun being above the horizon. Okay. So, that is we have dealt in detail how to deal with this sort of a situation, and from GON on the horizontal surface is GON cos theta z, and over a period of time like 1 hour from T1 to T2, that is designated by I0, which will G0 dt, and when you integrate it with GON is equal to GSC into 1 plus 0.033 cos 360 n by 365 multiplied by this cosine theta z, you will have a wrong expression for your I0 over here, and then you can have for the day by integrating it from minus omega s to plus omega s or twice of 0 to omega s. So, it will be the similar expression, except these hourly values of omega to omega 1 are replaced with omega s. It will be a twice omega s, that is why this 12 becomes this particular 24. And of course, the angstrom type of relation H upon H0 is A plus B by number of bright sunshine hours by the possible sunshine hours. This A and B are location dependent, or location or climate. This is measured with a sunshine recorder. So, you know a strip that gets burnt or NB, the bright sunshine hours, upon the possible NS sunshine hours for the location for the particular day, and you can correlate with the extraterrestrial radiation H0, which is calculable analytically, to the solar radiation on the Earth's surface. It is a crude approximate relation, but nevertheless the sunshine recorder has the ability to record and give you the NB without external power. So, then we have gone through a large number of correlations. For that, essential and key ingredient is the clearness index, KT. On a hourly time scale, it is I by I0. I is the component measured on the terrestrial, which will consist of the direct radiation plus the diffuse radiation, or you can base it upon the day, which upon is H upon H0, or KT bar, the monthly average daily value, H bar upon H0 bar, and this H0 bar will be calculated with delta equal to delta m, where the recommended mean declination values are given in the books, or in case you do not remember or you are not supplied, you can use the midday of the month for calculating delta mean. So, you have got first of all a ID by I, a function of clearness index due to Orgel and Hollands, Orgel and Hollands. Now, you might be wondering, what is the purpose of these things? Why? Why should we have this relation when we have ID and I? Most of the time, the measurements are and ID almost no for IB. The direct radiation, if you want to measure, you should align it with the direction of the sun's ray and have a tracking mechanism, and any small error in the tracking is likely to lead to a larger error. So, what is normally done is measure the global or the total radiation and the diffuse radiation, which can be obtained by shading the direct radiation part of it, and if this is not available, only if this is available, then my correlation for ID by I as a function of the clearness index KT will help me obtain ID from I. So, you can generate the diffuse radiation component from the global radiation if you have a correlation, and apparently Orgel and Hollands correlation in terms of the hourly clearness index is reasonably good, though there are improvements over this which contain ID by I, a function of KT and maybe theta z at that particular hour. So, people try to distinguish what is the path that the sun's rays will travel through this angle of incidence, which will depend upon the season and the location. So, Colares, Pereira and Rabel, they have given the relation for the daily diffuse fraction and the monthly average daily diffuse fraction, HD by H bar and HD bar by H bar. So, these relations I have shown over here, Hd by H, and then the next one is in terms of Hd bar by H bar, which is a function of clearness index for the month Kt bar. And then the detail of radiation So, these correlations one should understand that they are developed if you do not have the data detailed, how to generate some data which will mimic the tries to mimic at least in reasonable error limits the actual data, or it may be extremely convenient to computer implement. So, your RD first is due to ID by HD, Lu and Jordan. So, it is nothing but ID by HD is given in terms of this your relation pi by 24 cos omega minus cos omega s into this much. And by the way, this is also identically equal to I 0 by H 0. If you take the extraterrestrial radiation and the corresponding daily extraterrestrial radiation, that will turn out to be the same relation. Though it is a surprising thing how the extraterrestrial radiation, which is comprises of purely direct radiation, is so well correlated to the diffuse radiation, okay, and not to the direct radiation. Nobody talks about something like RB equal to IB by HB, does not exist. Maybe because the measurements are IB are limited, that could be a reason. Then RT similarly is I by H developed by Colares, Pereira and Raoul. Okay. So, this is in addition to the same term of ID by HD, you have got in terms of pi by 24 times A plus B cos omega times cos omega minus cos omega s upon sin omega s minus 2 pi omega s by 360 cos omega s, and you should remember omega s is in degrees. Okay? And the constants A and B are in terms of function of omega s. In other words, day length influences RT. Then, like any statistical distribution, Lu and Jordan again, so they have given a cumulative frequency or fractional time versus Kt, a daily or hourly, or I will write small kt. This is for Kt bar equal to 0.3, this may be for Kt bar equal to 0.7, this may be approximately 1 and this is 0. So, what basically it means is, if you take a month for example, there are 31 days or 30 days. So, you have daily clearness indices Kt1, 2 KT 31. So, I can, it is not necessarily the first of the day of the month is the lowest, but there are 31 values, out of which I have got changes from KT minimum to some KT maximum. So, if the cumulative frequency can be defined as the fractional time or the number of days below which a particular value of clearness index occurs. So, for example, if KT max is there, all the days will have a clearness index less than KT max, and if KT minimum is there, there are no days with KT less than KT minimum. That corresponds to that fractional time being 0, and this corresponds to fractional time being 1. So, it is something like your marks in the class, if there are 100 students or so, and less than 10% there may be 20 fellows, and less than 30% there may be another 10% fellows, and less than 90% everybody may be there. Okay. So, if you plot that, that will give you the so called occurrence of cumulative frequency or the fractional time or fractional distribution. So, these curves are developed with the North American locations, and they are more or less acceptable for quite a few climates, although there have been number of reports which show that they do not work for such and such a climate, for such and such a climate. So, in fact, our own investigation, we used a KT bar cap and a KT cap, which will be defined as KT minus KT minimum by KT max minus KT minimum. Similarly, KT bar cap will be KT bar minus KT minimum upon KT max minus KT minimum. So, the x axis remains the same, fractional time f, and you have got a KT cap over here, and the functions they look similar. This is KT bar cap. So, what we try to bring in here is by putting that KT minimum and KT maximum in defining these modified variables, you are taking that location specific characteristics. For example, if you have a Chennai and if you have the average clearness index of let us say 0.72 in summer and KT min may be 0.69, KT max may be just 0.74 against, for example, you have a let us say Srinagar, assuming KT bar in some month is 0.72, this may have a KT min of 0.33 and KT max of okay, it should be more than that, 0.78, okay, one particular day. So, you have got a large swing if the location is different compared to a low latitude location like Chennai. So, this will be taken care of in this type of plots, whereas low and Jordans will not in general accommodate the varying low and varying high clearness indices for a given average. So, we try to express the solar radiation on a tilted surface as consisting of the direct radiation plus the sky diffuse radiation plus the ground reflected radiation. and of course, overall factor R, if I t is equal to R into I, can be rewritten as 1 minus I d by I. Though it is a simple relation, I chose to show this in the summary with a specific idea which follows. You should see that everything is written in terms of I d by I, which are correlated to clearness index. So, if you have a measurement of only I and then the use of the correlation of I d by I or H d by H is very much understood. Then this R b is cos theta by cos theta z, which of course, where you have got your cos theta is a plus b cos omega plus c sin omega, as we have already explained, and then where a, b, c are given, and R b for a south facing surface is simple, like R b equal to cos phi minus beta cos delta cos omega plus sin phi minus beta sin delta by cos theta z, which is cos phi cos delta cos omega plus sin phi sin delta. All right. So, these relations I am giving it again and again, so that you should become familiar or not be just afraid to look at long expressions. There is a logic, the way we write it, the way we develop it, and if you pick up that, you shall be able to remember also. Though it is not necessary you should have them by heart, but you should be able to know the functions of it. Then from a solar energy collector, useful energy gain is expressed in terms of course, the area, the optical efficiency or the transmitter subsistence product, the radiation falling at the collector minus the losses evaluated between mean plate temperature and the ambient temperature. Ultimately, this has been rewritten in terms of the collector efficiency factor minus the losses evaluated from the mean fluid temperature, or in terms of the heat removal factor tau alpha times I t minus u L into T f I minus T a. So, by putting everything in terms of F r, I am able to have a single point temperature, so that there is no possibility of a misinterpretation or misunderstanding or miscalculation of TFM or TPM. So, you have got F dash is the collector efficiency factor, mind you it is not the collector efficiency, and F r is the heat removal factor, which have been defined in terms of the actual useful energy gain to the possible energy gain if the entire collector is at local fluid temperature, that is F dash. And your heat removal factor F r is the actual useful energy gain by possible energy gain if the entire collector is at the fluid inlet temperature. In other words, the losses cannot be lower than that corresponding to the inlet temperature, and if anybody gives more value than that, you can find out that the measurements have not been right. And UL is the collector overall loss coefficient, which needs to be calculated iteratively. You assume a plate temperature T_p and then guess a cover temperature, or for a given plate temperature guess a cover temperature, calculate the losses, and those losses should be equal to whatever is lost from the glass cover also. So, you can alternately calculate the overall loss coefficient by first estimating the top loss coefficient ut, a long expression. This has been correlated by Klein in terms of the number of glass covers, the wind heat transfer coefficient, emissivity of the plate, emissivity of the glass, mean plate temperature, ambient temperature, and of course, the Stefan-Boltzmann constant, and where this f and c are again in terms of other quantities like beta, the slope, and everything is explained over here. So, this can be readily used, and then you can calculate ut ul as ut plus ub, the back loss coefficient, which is nothing but the resistance inverse of the conduction or the insulation kept at the bottom of the absorber plate. So, if you go through a little bit of algebra, we got a simple expression for the heat removal factor, which I will give you in a minute. M dot Cp AC UL times 1 minus exponential AC UL F dashed by M dot Cp. So, if you look at this equation, my independent parameters are F for tau alpha and F for UL. So, we know how to calculate UL, we know now how to calculate FR, and tau alpha will be calculated later on. So, that your QU, the useful energy gain, is ACFR times S minus UL into TFI minus TA. So, that tau alpha, yes, we were talking about it, and well, it appears here. So, if S is the absorbed energy over a period of 1 hour, let us say, that should be equal to IT into tau alpha, which is tau alpha into I into R. Now, what we find is that this tau alpha comprises of the direct radiation component contributed by the plus the diffuse radiation and the ground reflected radiation. We will come to it little later, and in the same context we define a critical radiation level, which you know it has become very essential in calculating the utilizability, which is basically, you can say that IT for efficiency is equal to 0 or QU is equal to 0, which by equating QU expression you will get FR UL into TI minus TA by FR tau alpha. Once again, I should remind you that there should be a hidden time factor delta t, okay, because I can now this will be watts, and IC in general is kilojoules per meter squared hour according to our notation. So, FR expression already we have given. Now, you can express fluid mean temperature T FM as TFI plus the QU by AC. It is only a rewriting of it, not that you can really calculate by this equation. You can't do that unless you know QU. And the plate temperature is TFI plus same thing QU by AC by UL into FR times 1 minus FR. So, subsequently we have analyzed for a number of other configurations, not just the fin and tube, but different arrangements for the liquid based as well as the air based collectors, and we tried to take into account the heat capacity effect. With certain approximations, the temperature of the plate Tp varies with time as given by this equation. If UL is the overall loss coefficient and Tpi is the initial temperature and Ta is the ambient temperature, is related to e to the power minus Ac UL time by m Cp effective, and this mCp effective is mCp of the plate plus sigma Ai mCp I. So, I is equal to 1 to n. If there are n number of glass covers, we are trying to convert that into an equivalent plate by putting that mCp effective is that of the mCp of the plate plus this is the ratio of the overall loss coefficient from the cover under consideration to the ambient to the overall loss coefficient. So, Ai is Ui by UL. Then for air heaters, pressure drop could be a issue. So, we gave some formulae to calculate the pressure drop as if it is a duct, which is quite okay. And then the other geometries, the tube can be below the absorber or above the absorber, as we have shown over here. Fin and tube arrangement 2, that is what I call. Then of course, the corresponding efficiency factor is given over here. There will be slight variation compared to what you have for the first configuration that we have studied. Let me, this seems to be okay. Yeah. So, you have got f dashed, and the very first configuration we studied was with the tubes below the absorber, and this one is above the absorber. There are plus and minus points, because some people argue that this tube will be absorbing directly the solar radiation, but some people also argue that it can directly lose also by emission. Basically, it is a convenience of the manufacturing, and you have got of course the classical halfway. So, given your UL is always equal to the top plus the back loss coefficient in these arrangements, and I have again given there will be slight differences in the expression for f dashed, because how much of area it directly receives and it does not, and the fin efficiency is similar 10 HML by ml, as you know from equation, where your L is W minus D by 2. So, then we considered the air heaters. So, you can have a flow insulated glass cover. This is the absorber. The flow is between the absorber and the top glass cover. So, now the hot fluid is directly in contact with the glass, which loses energy to the ambient. Consequently, your so called overall loss coefficient UL is not a completely loss, but actually it goes to the fluid too. And you have expressed UL, and if you put UB equal to 0, UL will not reduce to UT in this particular instance. And collector efficiency factor, then the radiative heat transfer coefficient. The next one is the regular duct. You have the glass cover and the duct through which the flows, and of course you have insulation. So here is UL equal to UT plus UB. So there are no issues. So you have got a F dashed efficiency factor and the radiative heat transfer coefficient, and this is to have a heat transfer augmentation, particularly for air collectors. People provide sort of corrugations or the paths in between. So, this will break the sort of boundary layer or mix the hot and cold fluids from the bottom and the top within the duct, thereby improving the heat transfer between the fluid and the absorber plate. So, this is analyzed in terms of the spacing H1 and H2 are the heat transfer coefficient, and the expressions are over here. So, now you can define the fin efficiency of the plate and fin efficiency of the fin, because when I talk about these two, this is the fin efficiency of the plate, and if you take this as a fin, this is the fin efficiency of the fin. Okay. Now, people try to improve the heat transfer characteristics, particularly for the air arrangement, by having the flow through a corrugated sheet. So, if you have a corrugated sheet like this, of course, like the configurations we have discussed, it can be through this or it can be through the top, and there may be a glass cover. What this corrugated sheet does is effectively it will have a higher absorptance, because there will be re-reflection between these two surfaces, but then high absorption also follows by higher emissivity, though that is at a lower temperature. Consequently, still the gain may be little more than the loss, and but provides a much larger area for heat transfer, and then continuously the boundary layers are broken by these corrugations. So, here also it is not directly coming in contact with the heat losing surface. So, UL is equal to UT plus UV. So, this is a inside the tube which we have done. Then F dash, the collector efficiency factor, is given over here. Serpentine tube arrangement, the advantage is it has got the fin efficiency, plus also at the expense of the pressure drop, though the entire fluid will be going through the pipe, thereby your heat transfer characteristics may be better, though there will be additional pressure drop also. This is done by Abdul Khalik. So, these relations we have given in detail in the class notes on the earlier lectures. This is once again a large surface area trying to mix the hot and the cold fluids, a geometry due to Selkirk. Then a matrix arrangement has been suggested by Hamid and Beckman, and of course, the advantage here is the flow goes through this matrix like some sort of a porous medium having a large exposed area for heat transfer, though the pressure drop could be higher. And this is what we were comparing the so called evacuated tubular arrangement when we were considering the economics, the cost per tube of the evacuated tubular arrangement versus the flat plate collectors. So, then we went through concentrating collectors. So, there are different concentration methods, which you may find it here is simple, rather they are something like two boosters, and then you may have the central receiver concept or a paraboloidal dish at the focal point being the receiver, and a Fresnel lens or a Fresnel reflector. So, the necessary condition for the concentrating collectors is they need to be tracked. In other words, they should be pointing towards the sun. Perfect is 2 axis. So, if you have got a parabolic dish and here is the sun and the outer normal is always in line with the sun's rays. So, that requires moving from east to west as well as swiveling around a north south axis. Other simpler trackings could be first mode, which is one single daily adjustment such that theta is equal to 0 at solar noon, omega is equal to 0. So, that gives a simpler expression for this, gives the condition phi minus beta should be equal to delta, and you have got cosine theta, a simpler expression than whatever we have for this. Essentially, it is a flat plate turned towards south with a particular beta changing from day to day depending upon phi minus beta is equal to delta. Then this is again same thing, but I want to minimize at every instance, so that my beta will be changing continuously throughout the day, and you have got a cos theta. So, east west axis with continuous adjustment. Excuse me. So, this requires a continuous adjustment throughout the day, and of course, you can derive the expression for beta, and cosine theta expression is given here for this mode. And then you have got the third mode, a north south horizontal axis, which will have the cosine theta in this particular form. This once again you can realize for the third mode. Mode 3, you choose gamma is equal to plus or minus 90 degrees depending upon the forenoon or the afternoon, because it is whenever it is facing rotated from east to west on a north south axis until forenoon or the noon, it will be gamma minus 90, and after noon it will be gamma is equal to plus 90. Then the polar mount you have got, it is as if the collector is rotating along with the earth, and cos theta is given by simply cos delta the figure is shown over here, and you can see that depending upon the equator and the plane of rotation, which differ by an angle delta, my cos theta will be equal to cos delta, which is pretty good compared to perfect tracking, where you have got cos theta is equal to 1, because delta maximum is only 23 degrees and which will be almost 0.95 or so. So, consequently, cos theta being about 0.95 or higher compared to cos theta being equal to 1, there is not much of a loss in having it is only single axis tracking compared to perfect 2 axis tracking. So, in all these cases we need to calculate the what shall I say, the apparent sunrise and sunset hour angles for each mode 1, 2, 3, 4, 5, they are given. By setting theta is equal to pi by 2, you will obtain those numbers. So, we shall continue with the remaining of the summary in the next class, and I shall just go through the remaining relations, so that you will be confident, and these are all at one particular place for you, so that we can always refer to them. And once again, my offer is open. If you point out any mistakes, they will be corrected, and the correct answer will be, I shall communicate to you. Thank you.